the conversation started off about football. And unfortunately, the team I support is mostly useless. And we moved on from football to work. And that's really where it came across. Right? So after the beer had been drunk mostly.
And we suddenly realised that we had something in common, and that thing was iron, although we came to it from entirely different places. But we had a lot of conversations, and we realised that we actually had, if we put together the concepts that Jon was familiar with and the concepts that I was familiar with, and we matched them up, we actually came up with something that appeared to be original and excited both of us. And so we turned it into a manuscript.
My name's Jon Wade. I'm the Associate Professor of Planetary Materials in the Department of Earth Sciences at Oxford. Well, my interest was really understanding how the Earth's core formed. Why is the Earth different to, say, Mars and Venus and Mercury in terms of its iron content of its rocks? And that's really where Hal's interest in iron kicks in, and that's where the overlap is the iron in the rocks becomes the iron that life uses.
I'm Hal Drake Smith. I'm Professor of Iron Biology at the Weatherall Institute of Molecular Medicine, and my lab works on the role of iron in the immune system and how iron deficiency happens and how anemia happens and how iron influences infectious diseases. Iron's really useful in biology. It's absolutely critical for mediating catalysis and metabolic processes. So it appears when you go back in time and look at very ancient organisms that still survive today, you can see that a lot of the basic building blocks of biology are iron dependent. So things like generation of energy, making DNA, carrying oxygen in the body and in cells, all of those need iron, and that's the same for almost every single form of life. The paper kind of comes at this as a narrative tale of different roles of iron in evolution of life.
Iron is cosmochemically abundant. It's the last thing that stars make before they go pop or sort of stop being useful stars. So it's cosmochemically very abundant. That is, there's a lot of iron kicking around in the universe at this point in time. The amount of iron in the planet is really, in the rocks, is really governed by the processes that go on right at the very, very start of planetary formation. So as the Earth's first forming out of this sort of planetary building blocks, these meteorites, it's been sort of all falling together and starting to heat up and melt. The amount of iron in the rocks is really governed by the chemical and physical conditions of that process. You then have a very different atmosphere at the dawn of the planet than you have now. It didn't have any oxygen in the atmosphere. And the consequence for that is that in the early seas, in those deep Archean seas 4 billion years ago, when we know we have water around, iron was soluble in seawater. So there was about 5 orders of magnitude more iron floating around in those seas when life first started to get its act together and form than there is now, because of the rise of oxygen.
To begin with, iron is absolutely critical for setting the conditions that life can develop, and it's soluble in water and it promotes biochemistry, and so simple life can get going. But then you take the iron away. What happens then? You have to adapt, and any behavior that enables an organism to get hold of iron when it's difficult to get hold of is going to give a really big selective advantage.
This event around 2 billion years ago, this was what we term as the Great Oxidation Event, and it wasn't that great, but there's a bit of oxygen ends up in the atmosphere, and it's a small amount of oxygen, but actually has a massive consequence for the amount of iron, certainly the amount of iron in the surface seawaters of the seas around at that time, because that iron then becomes oxidized, and oxidized iron isn't soluble. It just rains out. And we see this in the rocks. We have these things called banded iron formations. They occur throughout history, but there's a big sort of peak of them around about 2 billion years. And that's this kind of soluble iron raining out. And that it has implications for life. And that's really where Hal's interests, or then Hal's sort of research really kicks in. It's around that point. You've got this evolutionary sort of driver. You've got this resource limitation that the Earth has imposed on life. And to some extent, life has imposed on itself.
What Jon and I were realizing when we were talking about the oxygenation event, the Great Oxygenation Event, and then the subsequent one, the Neo-Proterozoic Oxygenation Event, is that this was having an unbelievable effect on the amount of iron available at planetary scale. gigatons of iron were relatively suddenly becoming unavailable to the areas of the planet where there was most life, so the photic zone and the surface of the planet. What effect would that have? And it's really hard to know, but what we do know is that it was at that times that the evolution made enormous bounds. So development of eukaryotic life, multicellular life, evidence of predation, infectious events, symbiosis, all of these things appeared to occur after the oxygenation events of the planet. So these are big evolutionary leaps. And of course, evolution is really complex, and iron can't possibly be the only thing that really is governing this. But I don't think anybody, as far as we could tell, had really thought about iron in these terms as a kind of a planetary scale event and affecting evolution.
How life has dealt with these environmental restrictions it's had placed on it, this loss of iron. And it's come up with some quite nice mechanisms like, sharing and cooperating and have some of my iron and have some of your iron. But it's also come up with some quite aggressive ones that have also been very successful.
One of the things that we study in the lab is that these days iron's actually very hard to get hold of as an organism because it's insoluble and it's not floating around in water. And usually one organism tries to steal it from another. So you can't get it from the environment, you've actually got to steal it from another organism. And that is infection. And infection is essentially, if a bug infects you, it isn't interested really in killing you, it's interested in stealing your resources, using you as a source of food. And a key nutrient that organisms need in that concept of infection is iron. Iron is the most important nutrient that host and pathogens fight over. And so we were really familiar with this concept. It's something that we think about, on a daily basis in the lab in terms of an infection in a person and the genes and cells that mediate the response to the infection.
And I think that's what I found really, really interesting, is life is telling us about events that went on in Earth's rock history that we don't record within the rocks.
One of the probably very first interactions that iron has in the context of developing life is with sulfur. And still within us, in our cells, in our mitochondria, you have iron-sulfur clusters, little tiny, tiny little crystals of iron and sulfur in the middle of our proteins still.
And those iron-sulfur complexes, they're also recording those early reduced oceans where iron sulfides, FeS, is much more prevalent than in today's oceans which are oxidised. Where you do find it is in things like the bottom of the Black Sea, what they call these euxinic sort of seas, which are sulfide rich. But again, it's recording a very, very different environment. And that is kind of cool. Earth's kind of an annoying planet in some respects. If you're a geologist, it is quite annoying because it's really active. There's not many really old. There's bits of rock from all through Earth's history kicking around the surface, but there's not much. The further you go back, there's less and less of it. It's the selection pressure for rock, the preservation potential. So actually, we don't have a good record of what the Earth was like in the rock record 4 billion years ago. But it turns out that I think this is kind of an interesting thing. It turns out that life has recorded, at least to some extent, the chemistry of the early seas. We don't have bits of the early sea around, but we have it within us. So the reason life has used iron so extensively is because that's where it learned. Iron was available when it learned its initial programming back in those Archean seas that contain lots of iron. And then it's had to learn how to deal with an iron loss of 2 billion years and 800 million, 500 million years ago at that Neoproterozoic event. So I found that kind of interesting from a geology perspective. We're all into our rocks. We like going out and looking at rocks, but it turns out that we don't always have the rocks we want. And we might have to look at other evidence of the environment that was around for 3.5, 4 billion years ago. And that's where life kicks in, because we record within us some of those sort of grand events. Often we're not aware of what goes on in other departments and what their capabilities are. So again, this is one of those areas or things we have a common interest, a common story. We can tell a common story, and then we can bring the tools that we have that we're familiar with and answer somebody else's problems, or at least try and attack them. And that's exactly what we're doing at the moment.
Cross-disciplinary research is just really exciting, and it actually takes a long time to be able to speak each other's language, where even the same words that Jon would use that I would use, but we had attached entirely different meanings to them because we're from different fields. So, the intellectual interaction required some lubrication and time. But we got there, so then we did come up with something that I think is interesting. When I presented the work to people in my field in biomedicine, they found it very useful to get this perspective of, okay, we've been working on iron for decades, but why is iron so important? And it really does go all the way back to geology, planetary formation, and then great oxygenation event and taking the iron away. This is where it all comes from.
Joking aside, it's really important to sort of step outside your comfort zone and talk to other people and find what they do. And actually, this is a good occasion of an idle chat over a beer, which led to something very interesting.